All right, we had a bunch of questions that were homework for today, page 553, and we have to go over quite a few of them. 3, 4, 5, 6, 7, 8, 9. We'll go over number 3 first. How is the direction of the electric field defined? Somebody can give me an answer to that. I know there was a couple of people that had a question about that, but I also know that there's people that know the answer to this question. Caitlin, how do you define it? Good. And you used one word that's real important there. The direction of the positive particle would get displaced in the field. So if we've got, let's say, an electric field right here, a producer. We don't know what that producer is, but it's positive, okay? And we know that a little positive particle is pulled toward that, okay? Then we must know that this is going to be a negative particle because it's going to attract the positive, and the field is going to point toward the negative producer, right? Because the field is defined, as Caitlin just said, as the way that a positive particle would move if it was placed in the field. Now, if we take that positive particle away, that doesn't change the field, right? If we think about gravity for a second, you put a pen in a gravitational field and it falls as a result of gravity. If you take that pen away, gravity still acts down. Whether the pen is there falling or not, gravity still is acting down. So we've taken that positive test particle away. The field still points toward the negative producer. The field is the way that a positive particle would move if it was in the field. In other words, it's going to be toward a negative producer and away from a positive producer. All right, number 4. Why is the electric field classified as a vector field? This one's almost coming back to the definition of a vector, right? Vector has direction. Some fields influence us not in a particular direction. Some fields influence things in a particular direction. Gravitational field and electric field are both vector fields because they influence things in a very particular direction. There's a direction associated with their influence, as opposed to just the influence itself. 5. If vector arrows can represent an electric field at a point surrounding a charge, identify the 2 ways that the vector arrows shown below represent differences in the electric fields around the 2 source charges. All right. So we got 2 diagrams here. Diagram number 1 in the black square, and we'll make diagram number 2 in the green square. What are 2 differences with regards to these 2 electric fields, these 2 vector fields? That's your hint right there. These 2 vector fields. What are the differences? What's one of them? One of them is staring you right in the face. Well, really, both of them are actually, but Simon? The direction, right? Vector fields have both magnitude and direction. The direction is clearly different. The electric field in the first one is pointing directly toward the producer, and it's pointing to the left. The electric field in the second one is pointing away from the producer, and it's pointing up and to the right. So the direction is clearly different. What else is different about these 2 vector fields besides the direction? Again, your hint is still vector. They're both vector fields. We define a vector as a quantity with both magnitude and direction. What else is different besides the direction? The magnitude. Look at the length of them. The length of the first one is quite a bit longer than the length of the second one. That means the strength of it is quite a bit bigger than the second one. Okay, the length of the vector is proportional to the strength of the field. If one's longer than the other, then it's a stronger field. So we got 2 vector fields. One of them is bigger than the other one, and they're in different directions than each other. All right, number 6, I think, was the next one. Describe the effect on the electric field at a point if the magnitude of the charge produced in the field is halved. You know, let's copy this one over to get some more space on this one. If the magnitude of the charge producing the field is halved, well, listen, whenever we're changing the value of a variable without knowing what the value of the variable was to begin with, we're going to use that little technique that I call variable value changing, which involves finding an equation that's applicable, that's relevant. And that equation in this case is going to be E is equal to KQ over R squared. If we're trying to find the effect on an electric field when we're reducing or when we're changing the charge of what produces the field, then we're going to use this equation. This is my original field. My new field is going to be K times a half Q over R squared, which becomes a half KQ over R squared, which of course is my original field. So my new field is going to be simply 1/2 of what my original field was. Okay, that's a relatively straightforward one because we're not doing anything with squaring or anything like that. If we're changing R, then that's different. B, the sign of the charge producing the field has changed. Oh, okay. This isn't so much a variable value changing thing. What happens to the electric field if we simply change the sign of what produces it? It goes from a positive to a negative or a negative to a positive. Does that change the strength of the electric field? Let's say we've got a charge of 5 coulombs producing the electric field. That's a big charge, so it'll produce a really big electric field. But let's say that's what it is for argument's sake. Let's say we change it to negative 5 coulombs. Does that change the strength of the field? No, it doesn't. What does it do then? Anything? It doesn't change the magnitude of the field, but it does change the direction. Right? Again, the vector field that has both magnitude and direction. It's changing the direction of the field. And C, this is a hard one, actually. C is a hard one. Describe the effect on the electric field at a point if we change the value of the charge, the test charge. So our equation E is equal to F over Q. This is my original field, right? My new field is going to be equal to F over, what are we doing? We're cutting it in half. 1/2 Q. So that's going to end up being 2 times F over Q, or 2 times my original field. Does that make sense? Who got that? Who got that as an answer? Nobody? Good, because it's wrong. This is a hard question, but yet it's a simple question all at the same time. Let's go back to fundamentals here. Forget about the mathematics, bless you. Forget about the mathematics. Let's look at just the fundamentals of what's going on here. We've got an electric field. Let's draw a picture here. Okay? We've got an electric field right here. Okay? Let's say its strength is, let's say 2.0 newtons per coulomb. We've got a charge here that's, I don't know, let's say it's 3 microcoulombs. Is that 3 microcoulomb charge producing the field or experiencing the field? There's something over here that's producing it, right? This guy's experiencing the field right there. What if we change it to 5 microcoulombs? Actually, let's just add another one in there. Let's keep the 3 microcoulombs in there. Let's just add the 5 microcoulombs in there. What's the field now? The same. Okay, let's say that we have a 35-pound, one of my sons is 35 pounds. He's in the Earth's gravitational field. What's the strength of the Earth's gravitational field where my 35-pound son is? 9.81 meters per second squared. Now my other son, who's 85 pounds, jumps into the same gravitational field. What's the gravitational field where my 85-pound son is, who's more than twice the weight of my 35-pound son? What's the gravitational field there? 9.81. It doesn't matter how heavy the experiencer is, the field is going to be the same because the field isn't caused by the experiencer, the field's caused by the producer. Same deal here. If we change the charge of the experiencer, what difference does it make? The field is caused by the producer, not the experiencer. So we're not going to find the new electric field because of a change in the charge of the experiencer. The electric field is going to stay the same. The experiencer doesn't affect that. So how do we resolve that mathematically here? Okay, we go and do this mathematically, it doesn't work out. Math has to work out, doesn't it? Here's the problem. Here's the thing we overlooked when we did it this way. The charge does get cut in half. But because the charge is cut in half, the force, it doesn't say this, but the force is also cut in half. Let's think about that. Let's say my one son is 40 pounds and my other son is 80 pounds for argument's sake. If the mass of one son is half the mass of the other son, the field strength is the same. But the force acting on my one son is half the force acting on my other son. So if we cut both of them in half, and although it doesn't say it here, that's really what's happening. We cut both of them in half, we end up with exactly the same electric field. Does that make sense? I don't know if you'd see a question that's that tricky on a test or an exam or not. Well, I know whether you'd see it on a test or not, I guess. I don't know whether you'd see it on a diploma exam or not. I kind of doubt it, because that's ugly. Like that's a question. I mean, as simple as it seems when we go over it, that's a question that probably 85% of people in Alberta would get wrong, because they'd do what we did first, right? They'd say it's twice the electric field. Remember, the experiencer doesn't affect the electric field. The electric field affects the experiencer. Got it? All right, that was number 6. We've got number 7 as well. So it says, given a small sphere with a positive charge of 4.5 times 10 negative 6 coulombs, determine the magnitude and direction of the electric field at a point 0.3 meters to the right of the charge. So let's draw it out. Right? We always like to draw these out. It just seems like it's simpler if we draw them out. It's easier to visualize. Right, Caitlin? If we draw them out. So this is going to be 4.50 times 10 to the minus 6 coulombs. And we want to find the field strength over here, 0.300 meters to the right of it. Now, I don't know if there's an experiencer there or not. It doesn't matter. We have enough information about the producer to use the producer equation. So let's do that now. E is equal to KQ over R squared. Don't forget the 10 to the minus 6 there when we plug this in. 4.5 times 10 to the minus 6 divided by 0.300 squared. And what do we get when we do the math on that one? Someone's got to have that. 4.5 times 10 to the 5. We could say newtons per coulomb, which is what we usually say, but we've also now learned another set of units for electric field, right? We learned yesterday, volts per meter. Okay, so I'm going to put newtons per coulomb because that's the most typical units that we see, but volts per meter would also work there now. Good, thank you, Caitlin. B, the magnitude and direction of the electric force acting on a positive charge if placed in that field. So let's put a positive charge right there at that point in the field. It's an experiencer. So now let's use the experiencer equation to analyze this. E is equal to F over Q. Remember, we've got 3 equations for the electric field now. Okay, the producer equation that's in blue there, the experiencer equation that's in green, and then we've got that other producer equation, but the one that's valid only for parallel plates. These 2 equations are valid when you have a non-uniform field. That's what we've got here. A point source producer that's a non-uniform field. So we can use them both. It's just a matter of looking at the givens. All right, we want to find the electric force. So let's rearrange this, and let's say F is equal to Q times E. We're dealing with a positive charge of 2 times 10 to the negative 8. And we're dealing with an electric field. We just found it. It's 4.5 times 10 to the 5. The electric field produced by the blue charge there at this point is the same as the electric field experienced by the green charge at that point. It's just like gravity again. Maddie, what's the gravitational field that you're experiencing right now? 9.81, good. What's the gravitational field produced by the Earth at the point where you are? 9.81. So the field that's caused by the Earth is the field that you experience at that point. The field that's caused by the blue producer is the field that's experienced by the green experiencer. That's why we can take this number and put it into here. Okay, that gives us about 9 times 10 to the minus 3 newtons. And what about the direction? Well, we always know that an electric field goes away from a positive producer. But we also always know that a positive is repelled by another positive. It's pushed away from another positive. So the electric force would be to the right in the same direction as the electric field. Next question we needed to go over was number 8. A small test sphere with a negative charge of 2.5 microcoulombs, and it's negative, right? An electrostatic attractive force, 5.1 times 10 to the negative 2 meters. It's placed this far away from another larger charged sphere. What's the magnitude and direction of the electric field at this point? All right, draw it out. Draw it out. It becomes helpful usually to do that. So we've got a charge here that's negative, 2.5 microcoulombs, which is 2.5 times 10 to the minus 6. It experiences a force of 5.1 times 10 to the minus 2 newtons. Right away, we know that that's an experiencer if we know that it experiences a force. It's 0.400 meters away from another larger sphere. Okay, this guy's going to be the producer, right? We don't know what its charge is, but it's going to be the producer. What do we know more about here? The producer or the experiencer? I think it's clearly the experiencer. So let's use, for question A, the experiencer equation. E is equal to F over Q. We're dropping the sign of the charge because we always do. Don't forget to make it 2.5 times 10 to the minus 6. And what do we get for that one? Thank you, Emma. 2.04 times 10 to the 4. And the units for that would be newtons per coulomb, or we could have went volts per meter for that as well. Good. The magnitude and the sign of the charge on the larger charged sphere. So the producer. Well, the field experienced by the little negative experiencer is caused by that bigger producer. So let's in question B use my producer equation. But let's take the value of the electric field that I just got from the experiencer and plug it into the producer equation because they're one and the same. We're solving for Q, so it becomes E times R squared divided by K. Okay, this times 0.04 squared divided by 8.99 times 10 to the 9, and that gives us whatever coulombs. How do we know what kind of charge it is, though? Because the equation will never tell me that, whether it's a positive or negative charge. Who thinks they know whether it's a positive or a negative producer here? There is something written in the stem of that question that will tell us quite clearly that it's either a negative or a positive. What is it? Good. Emma says because it experiences an attractive force. What does that mean then, Emma? Right. It's got to be a positive because that negative is not going to be attracted to another negative. Got to be positive. Kenton, that's what you're going to say too? Good. And finally, on this page at least, finally number 9. Negative charge of 3 millicoulombs. Here's one that we don't see all that often, a millicoulomb. Still a strange unit that we don't really like. It's to the right of another charge that's 2 millicoulombs. We want to find the field midway between them. Oh, 9b, there's a toughie right there. Mathematically, there's a toughie. Let's draw this out for 9a here first. We've got 2 millicoulombs. So we've got 3 millicoulombs. Not microcoulombs, millicoulombs, which is times 10 to the minus 3. We've got 1.2 meters between them. And we want to find the electric field midway between here. They're both negative. So the field caused by the first one is to the left. And the field caused by the second one is to the right. Field always goes toward the negative producer, right, Simon? Always toward the negative producer. So independent of the other one, independent of number 2, number 1 will cause the field to the left. And independent of number 1, number 2 will cause the field to the right. Let's get the value of both of those fields. We get 8.99 times 10 to the 9 times 2 times 10 to the minus 3, because that's a millicoulomb, divided by 0.06. No, not 0.06. Should be 0.6, right? Half the distance because we're looking for the field strength midway between. Who's got a value for E1 then? We get 4.99 times 10 to the 7 newtons per coulomb. We do the same math with E2, and we're going to get 7.49 times 10 to the 7 newtons per coulomb. We're going to add these up, but when we do, this one's going to be positive. This one's going to be negative. So we're going to end up with about 2.5. Uh, 2.49, yeah, 2.50 times 10 to the 7 newtons per coulomb. Right, the difference between those two fields. Well, that's the easy one. That's the easy question there. B is the hard question. Anybody feel like they may have gotten B? Anybody give B a legitimate try? It's a tough, tough question. I'd be surprised if you saw a question like B on an exam. I would, because it's tough. The mathematics is kind of tricky, and it would take you a while to do. But it's a good thinking question. We want to find the net electric, we want to find a point where the field would be 0. So here's my first charge. It's -2 millicoulombs. Here's my second charge. It's -3 millicoulombs. These are 1.20 meters apart. We want to find a field somewhere in between where the field strength is 0. So let's do this. Let's say this is my distance R. Okay, my point where the field strength is 0 is a distance R away from charge number 1. We don't know what that R is. That's what we're trying to find. We also know that this distance between the 3 millicoulomb charge and that point where the field strength is 0 is 1.2 minus R. That's a tricky thing right there. Why is it 1.2 minus R? Well, if it's R away from one of them, it's got to be 1.2 minus R away from the other one. Let's add these up. What's R plus 1.2 minus R? 1.2, the total distance that separates them. That's the first big jump you got to make here. Now, the next thing we're going to do, because the net electric field is 0 here, we know that the field caused by one of them is this way, field caused by the other one is this way. We know that those two fields have to be the same if the net field is 0. So let's set them equal to each other. The field caused by 1 is equal to the field caused by 2. Opposite in direction, but equal in magnitude. E1 is KQ1 over R squared. E2 is KQ2 over what? Not R squared. What's the distance from the 3 millicoulomb charge to that point where the field strength is 0, Tom? 1.2 minus R. Is that okay? So the field caused by the first one at that point is KQ over R squared. The field caused by the second one is KQ over the distance squared, but the distance isn't R, it's 1.2 minus R. Now, I don't know about you guys, but when I see this, I think, is there any way that I can simplify this at all? Well, there is one way to simplify it a little bit. K appears in both terms, so it cancels. It becomes Q1 over R squared. Q2 over 1.2 minus R squared. And the next thing I think is, oh my goodness, 1.2 minus R squared, that's going to be a FOIL thing, isn't it? You know what I'm talking about? You remember that from math class? And then it's like, no, wait a second. There's an easier way than to FOIL this. Let's square root it. Let's square root both sides. If we square root both sides, what do we end up with? We end up with square root of Q1 over R squared equals the square root of Q2 over 1.2 minus R squared. Are we allowed to do that? Doesn't seem to help. It seems to make things more complicated. But if you look closer at it, it doesn't actually. It's the square root of Q1 over r equals the square root of q2 over 1.2 minus r. All of a sudden, that square is gone, and we don't have to worry about the FOIL thing now. Q1 has a charge of 2 millicoulombs. So it's going to be the square root of 2 times 10 to the minus 3. This is 3 times 10 to the minus 3, the square root of that one. Okay, it's looking a little bit better here. Still kind of ugly, but looking a little bit better. So square root of 2 times 10 to the minus 3, 1.41. No, it isn't. Yeah, 1.41 times 10 to the minus 3, I think. Somebody check that, okay? You guys on this side of the room, Tom's side of the room, check that. I think the square root of that is 1.41 times 10 to the minus 3. Square root of 3 times 10 to the minus 3. You guys check what that is. I'm not sure what that is. Well, that's why I had you guys check it, right? 4.5 times 10 to the minus 3. And this times 10 to the minus 2. And this one's going to be what? Square root of 3 times 10 to the minus 3? 5.5 times 10 to the minus 2. Thank you. 1.2 minus r. All right. It's looking better. At least we don't have this square in there, especially the square that surrounds 1.2 minus r. That was the real ugly one. Let's simplify it even more here. Let's take this up here and this up here. 4.5 times 10 to the minus 2. Oh, look at this, actually. Hold on. Let's simplify things a little bit more. Something cancels here. What is it? Well, I like this. How about 10 to the minus 2? Here's on both sides. Let's get rid of it. Saves us from writing that out again, and saves us from putting it into our calculator. So now if we take this 1.2 minus r up, it becomes 4.5 times 1.2 minus r equals 5.5 times r. Now it's looking even better. Let's take the 4.5 over to the other side by dividing. 5.5 divided by 4.5 is 1.22. So 1.2 minus r equals 1.22 r. Let's take this r over, but to the other side by adding. 1.2 equals 2.22 r, right? 1.22 r plus 1 r is 2.22 r. Now let's say 1.22 divided by 2.22 gives me tell you in a second. Let me do it right on my calculator. 0.50, 0.54. All right. So what does that tell us? This distance here is 0.54 meters. The point where the electric field strength is 0 is 0.54 meters from the smaller charge. And that would make it, what, 0.66 meters from the bigger charge? Is that something we predict? Is it going to be closer to the smaller charge? Yeah, it has to be, right? If you want these fields to balance, and one of the charges is smaller, well, it's going to have to be closer to the smaller charge in order to get a big enough field to balance the other one. All right, that's a long and cumbersome question. I don't imagine anybody actually got that question. And I wouldn't even necessarily expect you to be able to get it if I gave something like that to you again. But did you follow it? Did it make reasonable sense as we went through it? Good. Then you know what? You're smarter than you were 5 minutes ago then. Even if you couldn't do this yourself, if it made sense to you, you're still smarter than you were 5 minutes ago. All right, make sure you get worksheet number 8 finished for Monday, please. Worksheet number 8 for Monday, please.